ये बेकार है।
ये 11 पार्टिसिपेंट हुआ।
खाओ 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 खाओ। हम ये रोटी नहीं खाएंगे। हम कल के बारे में तो एकदम बड़ा मैं बीमार होने वाली हूँ।
Just.
हाँ.
Welcome to the third day of this internal webinar on recent advances in science and technology. Uh, in this first session, Professor Srinivas Sethi of IIT Sarang will chair the session. In this particular session, we have 6 different speakers, mostly from nuclear physics and one from chemical engineering. So I invite Professor Sethi to chair the session. Professor Sethi, sir, please.
Thank you. Good morning to all of you. This morning session, the first presenter is Professor M. Bhuya from Malaysia. Okay. Mrityunjay Bhaja, presently Assistant Professor, Faculty of Science, University of Malaysia, Kuala Lumpur, Malaysia. His academic career includes FAPS, Postdoctoral Fellow, Institute of Technology, de Antarctica, São José Campus, Brazil. From 2019 to 2016, CAS Postdoctoral Fellow, Institute of Theoretical Physics, Chinese Academy of Science, China, Institute of Physics, Department of Atomic Energy, India. He received his PhD in Theoretical Nuclear and Astrophysics from the Sambalpur University. And in Institute of Physics, he pursued his MSc Nuclear Physics specialization from the Sambalpur University, India. The research area of the mainly focus on the nuclear structure and reactions studies using the various theoretical models. In addition, he also studied the astrophysical aspects such as neutron stars, Hypern star, their properties using the nuclear models. His research work has been published in the various international journals, ISI and SCCH CI Index, Physics Letter B, Physics Review C, Astrophysical Journals, International Journal of Modern Physics, Modern Physics Letters, Journal of Physics, Particle and Nuclear Physics, Physics of Atomic Nuclear Physics A, Ata Physics Planicam, Praman, a scientific journals, IEEE Springer, and also so many. He currently serves as an editor member of the 3 international peer-reviewed scientific journal published. The Journal of Nuclear Physics Science Publishing Group, USA. ACIREA Journal of Physics, USA. He has been engaged as reviewers for the various scientific peer review international journals, International of Modern Physics, Modern Physics Letters, Physica Sceptia, Canadian Journal of Physics, Modern Physics Letter, Letter of Physics, and so on. Last but not least, he has won the Young Scientist Award in Physics, Odisha Physical Society. In the present seminar, Professor Bhuya will deliver the topic that is binary neutron star manager events. That is constant on this equation of the state of nuclear matters of the supernuclear density. I hope it is very interesting one, and the audience will be enjoy a lot of in this presentation. Professor Bhuya, I welcome to you this sessions and present this your topic. Thank you, thank you, Bhuya.
Okay, thank you, Professor.
basically to introduce you with a great word to me. Pleasure for me to be here. So now I can share my screen.
Start.
It is visible to everyone, right?
Yes.
My screen can
Yes,
be visible
Professor
to
Bhuyan.
everyone? Okay. So, all right, it's a great pleasure for me to be here, and thank you to the organizing committee to arrange such a beautiful and also scientific event in this COVID pandemic. So, for example, like to teach in the home, we are doing science. So that is also extra. That is bonus for us to be have a conference like a seminar or maybe like some scientific discussion like this way. So, all right. Based on the plan, so my today I will going to discuss about GW170817. Basically, in the in the timetable as well as for example in the book that planning booklet also there is a little mistake in the title 101018. So it is with zero, not exactly one. Okay. So basically, if you go to here, GW stands for the gravitational wave and 17 is the date, 08 is the month, August, and 17 is the year. So that means the observation happened in 17 August 2017. This is one of the era changing observation by the LIGO and HIGRO, that gravitational wave detector, which is frequently working on the opens to observe all these phenomena. So that's why in the maybe this is a typo mistake in the booklet and also in the timetable given by. Maybe I did this mistake in the writing time. So I think the organizer have just used that. So this is my mistake in the title. Okay. So by the way, so this is a binary neutron star. So binary means two neutron star merger event. And what actually here more important is the constraining the equation of state of the nuclear matter at supranuclear density. Basically, supranuclear density is also one of the confusing. So what exactly is the supranuclear? So if you follow that, what exactly is supranuclear? So then things is that supranuclear has no limit. That what we have to say. But one thing we have to say, it is more than the saturation density. The saturation density, the density, the density of a nucleus, you can say, because if you tell in a very simple way, so the density of a nucleus. So saturation density of a nuclear matter is almost close to the value that is the density of a nucleus at the central region. So the density it is around a value like 0.16 Fermi inverse minus 3. So then in case of supranuclear, so it must be more than around 2 times or 3 times or 4 times of the density. Then we try to constraint. That means we try to modify the model to such a way that we can reproduce the data in a better way. That means we have to fit for the unknown region and higher density. Then we have actually we have to discuss a little bit on this point because these events basically the GW17 binary neutron star events they give a very beautiful picture corresponding to and also not only it is also very important to get information regarding the matter. So, okay, the outlook of my talk is like this way. So first I have to discuss about little the neutron star, and then we have to go for the gravitational wave events. What is basically if you are going to the neutron star, it's very well known to everyone because from the 1930 or earlier we have the imagination of neutron star. So even at that time, even we do not know about nucleus properly, but we have the imagination of neutron star. It's a very it shows that how intelligence of thinking we have in the physics society. So then there is the density dependent Van der Waals model. This is a theoretical model. As a theorist, it is one of the important facts for me to discuss the model. So here is the important Van der Waals model you all know, but to apply the Van der Waals model to the nuclear for the nuclear system, it is also one of the challenging for us. And if you see the Van der Waals, it's basically equation So that's why it is more realistic calculation. One kind of, you can tell what is one of the realistic calculation for the nuclear system to study. So then the applicability of the BDW means the density dependent Van der Waals model. So actually the original Van der Waals model, which is modified by us, and this modification is known as density dependent. So how we modify, how we introduce the density, all things we try to cover in this talk. And then we go for the tidal properties of the neutron star, the tidal deformability, Love number, that and many related quantities we have to discuss in this. Then we try to make the possible correlations and remarks. So basically, based on the these two papers here, I have given these two papers. One is the Astrophysics Journal in 2019, and also Physics Letter B in 2020. My talk will be based on these two papers. So it is the two recent paper we have on Newton star merger, and basically we try to implement a nuclear application, how we modify the model and other details. I try to cover in this small time. So if you go, there is the collaborator. So I never to forget this, because without them this work will never to be possible. So there is three groups here. One is from Brazil group. At the time when I start this work in 2019, so I was in Brazil. So I was also belongs to that group at that time. So but then I lived to here, and I joined as a faculty at University Malaya. Then there is another group from the Spain, and there is other groups from India and China. Basically, Indian groups is from Institute of Physics. So based on the same, we have to discuss the few remarkable contents that I have tell to you here in the outlook in my talk. So basically, if we go, I have to hide this. Where is the hiding option? Okay. So okay. So when we are going to very basic things, because as the talk is more of the participants from the undergraduate and graduate level, so I think I have to give you a little introduction about the gravitational radiation and other things, because it will be helpful for the students. So that can be, because new theoretical nuclear model and development, it is always boring, more of the equations, derivations, so there is no charm of lot of things because in a presentation. So it's better to be have some presentation which can be give you the more interesting on that. So basically we try to understand what is the gravitational radiation basically. If you see very early sentence from the Einstein theory of gravitation or gravity, the accelerating so accelerating mass cause a fabric space and time. Basically, it is look like if you see that if you sitting near to the pond and say storm to the pond, then the tide producing the water or surface of the water come to the, that is the exactly the similar looking like a gravitational wave. So it is very, because why the space time ripple vehicle happen, that is also important. So we have to going to discuss on this point. So there is a many source for the gravitational wave radiation, but as we are concentrating here for the neutron star, so there is four important kind where the gravitational wave are radiated from the neutron star. So first is the inspiring binaries, that is means one two astrophysical objects to participate in that. That means either a black hole, one neutron star, or neutron star black hole, or a black hole, like that. This kind of system. So it can be explained in terms of a post-Newtonian approximation, that is Einstein's theory of general theory of relativity. So then we have to go into the supernova core collapse, that is found in nine, because it is a very energetic process, as well as also very the dynamic change in the process is very quick. So it is also very difficult to handle by the theoretical people. So another third type one is the rotating compact star. If the Newton star or compact star, because I'm writing the compact star here, because now it is the most of the theoretical predictions have comes to here, that the star cannot be like only content of neutron and proton. There is also hyperon and quark, all these things. So that's why you can call compact star. If there is a rotation happen, then due to the rotation, there is a change in the symmetry, because if you remember, actually what is this symmetry change? For example, any kind of a ball or little fluid type balls you take in it and try to rotate it. When the rotation happens, basically change in the shape, either in the prolet and oblet if you're talking about a normal finite nucleus. But when you are talking about a astrophysical object, we call these as eccentricity. Eccentricity is one of the ratio between the semi-major axis and the semi-minor axis. So that gives you a shape. Either it's oblate can be extended like this way or maybe extended like this way. When this kind of change happens, this will also give you a possible source for the gravitational radiation. Another one is oscillation and instability if it is superfluid, like when the quark, basically quark model predicts this kind of thing. Then there is a oscillation inside the matter, and that instability also gives you possibly there is a gravitational radiation. So all the things what we have here, basically all have the possibility that can be radiate gravitational wave. So what is the discussion I am giving here? GW11718. This is corresponding to that. That means inspiring binary. So okay, let's see. So if we are going to gravitational wave, so we must have to know that how the gravitational wave move or propagate. So in such cases, I have given a simple example because electromagnetic wave, all the physics people are already acquainted with the same. So if you are going to talk about the electromagnetic wave, then the oscillations is like in the x and y direction. For example, the this oscillation having in this, and it will make like an angle and moving in the z direction. So this is the propagation of electromagnetic wave. Gravity wave is almost similar. If you look at this, this is like two polarized electromagnetic wave, and only difference is that the gravity wave polarized in the horizontal with a plus sign or maybe 45 degrees to the x shape and make a x shape and also propagate like this. So if you from this you can we can see that how the propagation of a gravitational wave happens. Because it is important to detect a gravitational wave, so we must know that how it will propagate. So based on this, we there is something. Okay, sorry. So here I'll given little bit importance of the gravitational wave in terms of electromagnetic wave. If I'm going to the electromagnetic wave, so it is like accelerated charge. So charge particles are the participants in that. But here is the acceleration of the matter distribution. This is also one of the important things we have to remember. So this change the figure of physics. That means acceleration of matter distribution. That means matter inside. Second thing is that it is continuous emission in a day or month after merger. It is the instantaneous emission. It is one of the demerit maybe you can conclude. But highly interact with the medium. Here is the transparent in terms of no interaction, possibly not to interact. Here the frequency is like 10 greater than 10 megahertz. Here is the 10 kilohertz, less than 10 kilohertz. So our ear can be hearing. So gravitational wave we can hear it. So this is two important factors that matter distribution, and it is also another is the frequency. Tell us to see the universe, to define the universe, our interaction, whatever the models, whatever we have already done. So we have to think of once more again in this new era, along with this matter distribution and also the frequency. So basically, what is the principle? How we measure this gravitational wave? So people, 2017, it is the news in the all of the channel and world cover. That is one of the most scientific events. What is the capture that was in the GW170817 event, like a Newton star merger. So how we exactly we detect it? At the physics point of view, it is very normal. So I think most of us, not most, even all of us, we know that laser interferometer because we in our master study there is when we are doing our MSc master study we have laser interferometer in the laboratory to do the experiment. Maybe in Odisha, there is Fakri Mohan University has this facility. Other university do not have. But I'm talking about government university, but the rest of the university don't have. So laser interferometer, it is very normal when what happens is beam is coming and slipped into two different laser beams and sent down in a long path, and there is a mirror. If you are say you see here, there is a mirror then it will bounce back and recommend. If there is no absence of gravitational wave, here if this is that like that, there is no in the lab what we do experiment, it is external effect. So here is the effect is replaced by gravitational wave. Okay. So any kind of effect you want to measure, so this is the effect there. If there is no effect, then that means there is no gravitational wave. Then the arm length are arranged in the so light industry, no signal will be measured. But if this the same things happen, if there is gravitational wave, then the positioning of the mirror change. Then what are ultimately what we get? The arm length also change, and interference is no longer perfect. That means the perfect interference not happen. So some of the signal will be get as a output. So this is the very basic physics what we do in our undergraduate or graduate level in the physics. That is the physics behind of our gravitational wave detector. So that's why it is also called, the name is called like laser interferometer gravitational wave observatory, because of course it has more technique and more expensive things that we have to maintain, that there is no outside effect, everything should not become, so we can precisely try to measure the gravitational wave. So of course, but the physics is exactly the same. So here also I have given a schematic diagram. You can see exactly the picture what I saw here in the previous slide. So same thing, and you see, look at this. This is the hydro. This is the lower one. It is in the Italy, and this is in the gravitational wave to Washington, and it is at Livingstone, and there is also another similar crater also in Washington. So there is two observatory, because I am giving the importance for these two because they play the big role for this last detection of the GW170817 binary neutron star merger event. So more this image from the LIGO hydro collaboration. So I am not experimentalist, but still to understand the theory, then we must have to know the experiment better way. So it is totally connected with each other. So without information for the experiment, it will be hard to proceed in any calculations or any kind of thing. So let's have to see that we have, because like this is the world facilities we have, like this there is many facilities available worldwide nowadays, because after these events maybe that time the hydro is here Italy, and the LIGO these two here, they play the roles to detection of these things. But now there is also Geo 600 in operational. Tigra is in Japan. It is also in almost completed. It is going to operate soon. And LIGO India already approved, and maybe the construction already started. Because I do not know more updates, but I think this is news at around 2017. I am telling. So these are the things. It is approved already, going to have the observatory for the gravitational wave. So these are the detection facilities we have in the near future, and also which are operated at the present. So based on this, so when we going to see this, how the observation, basically what the observation they provide, because in the LIGO and hydro, if you're going to first the technical parts published in 2015, because I have to go to some of the significant contributions from the LIGO. So in the 2015, they give published a paper. It is based on the instability in the advanced LIGO. That means instability going to give you the accuracy and technical details of the detector, how to measure the gravitational wave and other. The test purpose, they also observe some of the binary that black hole merger and the frequency allow frequency also they have observed. In the third part, in the third paper, it was also very interesting. Neutron star dynamic and gravitational waves. So here they have mentioned here, because there is there is core collapse, supernova, and the merger of the compact star, the binary spiral. These are the important things, but among the best candidate source for the gravitational wave are oscillation, but mainly the rotational instability of neutron star. That means if a neutron star also rotating with some speed, that is also possibility to have a strong gravitational wave signal. This is also one of the physical study, and they also have some paper on this. So in after that, in this year, this is the events they signal the gate. This is this you can see in that blue. There is a signal you can see in the middle that is like this. Yeah. So if you see this, so this picture changes the total era of the system. Because if you see, then why we have to, this is the two papers coming, one is here, GW event observation in gravitational wave, binary Newton star. Here is the measurement of Newton star radius and equation of state. So these are, because here this paper gives you more information connecting to the equation of state which we study in the nuclear model. And here also give the details of the experimental observation what they get. And these two papers are the most cited paper for the year 2017, 18 and 19, 3 years. And continuously they get cited more than 4,000 numbers, like in total maybe more than 5,000 numbers. So that means in this paper that shows that how many people try to test their model and try to make efficiency or increase their efficiency of the model for the calculation of the matter, nuclear matter at high density. That means at supranuclear density or to study the neutron star. So that is the most motivations behind the present talk also. So if you see here, so there is many events. It is the pictures from the Hydro. Hydro is localized the picture from the events happens in the last few years. I have not mentioned the year. So here all the events, whatever, so this, or whatever the events you can see, then we have many gravitational wave events. Then what is the importance of this event? What is the importance of these events? So that we have to also understand. It is the most important factor for our study. So because if you go to this, these are all black hole mergers, or the binary may be like the black hole and like this. But here in the GW170817 event, it is Newton star merger. That is the first difference. And what we get exactly? Because if a binary neutron black hole or something they merge and they give a signal, but whatever the signal we get for the gravitational wave, so we do not get much information about the matter because as a black hole merger, we do not get much information about the matter. So, but here in GW 1708, sorry, 1708 17 event, this is due to the two neutron star merger. Then we get the more information about the matter, which connect to understand the nuclear theory, which is applicable for the nuclear astrophysics in a different way. Or maybe we try to get our model and we can try to judge or we have to measure what is the applicability of our model in the in at high spin and high isospin and high temperature and also high density. The three things we have to can be measured. So here I've given a beautiful video from okay. So here you can see a binary neutron star merger. It's animation by LIGO group, and it is beautiful to see this animation. You see the left hand side there is the matter density for the two neutron stars, and the right hand side they're showing the gravitational wave that is injected from the thing going to be here. So then when the merger, then it's the merging there, and if you see here, this is the merging, and there is also there is also one simulation of merging the neutron star, also done by Breu and Rosola. So if you see here, there is a time the temperature cell, here is a density cell. From this scale, you can see how the internal region can be quite glow like yellow, so high temperature, and here also this color is very high density. So in such density of such high, it is called like a ultra density, it is too high, okay? So in such density, it is possibility to have the quark. So in that high density quark means recombined state of quark can be found out. So this is some of the things we also know from that. So basically, the two Newton stars, those who are going to merge, this is like it is already expected to be from last 130 million or go. They are orbiting each other in the final momentum, because how they basically how the newtons are going to measure when they rotate in their final momentum, then what happens, they get closer, and the movement also, orbiting speed also, in spiral speed they also increase, and in that they try to they have to interact and colliding to share the matter, and these events happen, and we also get like it is a first direct measurement by the LIGO hydro to give the information about the gravitational wave. Second things also, they observe it for after two these events happen for like 100 or around 100 to 150 seconds, and they also observe for like 2 seconds or more. So that is the more technical things you can find also in the sites I have given to you, like in the LIGO and HYGO, in the picture I given to you. That more details information you can find, and it is also very interesting to join the experimental groups to work on this. They have also many career opportunity for the students. So by the way, in the same time, theoretical people, based on the margin, they also predict many different things, like it is like a glow, fireball, another thing, something like a kilonova events. Kilonova is like that when, for example, so kilonova is a phenomena when the material, when they have been going to join here, because if you see the in the star, we basically think that we have the reaction happens like pp chain, then proton proton chain, then we will go for the helium burning, after that it's going for the cno cycle, all these things. But here, due to high temperature and density, maybe there is a production of like gold and pb nucleus, and they can be come out from the central part of the collision. uh, that event when they come out will be like a very glow, and that is called kilonova event. So more technical things you have to understand about the neutron star merger. So then exactly we get from that. First of all, it is confirm the Einstein general theory of relativity, because the general theory of relativity like predict that the gravitational waves should be traveling the faster of the same speed of light. So this is not the first measurement that can be that can be proved that Einstein of relativity, but there is also gamma ray measurement before. We have also the information about the general theory of relativity, that gravitational waves should be travel at the speed of light. But it is one of the direct measurement, direct observation, as well as it also confirmed the previous predictions from the gamma ray measurement. So then there is also fundamental questions, like opportunity to understand the fundamental questions about the structure of the matter, because as it is Newton star model, it contains the information about the matter, and then as the central part of the things is high density and high temperature, so it is possible to have a phase transition where the Newton, because as it is a Newton star, so Newton resolve into the constituent quark and gluon. So that means if you know, it is very clear that proton and neutron contain the quarks, but in English confined state. But here you can have the information for the quark and gluon, because due to the high temperature, there may be the possibility have the phase transition. That is also one of the information is there, that we explain our fundamental. That is one of the more important and also fundamental questions to explain the universe. The second things are the neutron star. It is a very isospin asymmetry system. For example, neutron is matter. That's why I am writing this. Neutron is matter. So neutron is matter, because if you're going to neutron star, it's called neutron star, but this contain also fraction of protons there. So it is highly isospin asymmetry. So as it is highly isospin asymmetric system, so there is a possibility to get the neutron is matter, and which is also enhance the R process. R process nucleosynthesis. R process is the rapid process nucleosynthesis, because there is two or three kinds of process there: rapid process, slow process, and rapid and slow process, like this for the nucleosynthesis. That means elementary producing the astrophysical objects like neutron star or other. So in the R process, basically what happens? The electron capture process, no, the neutron capture process is more faster as compared to the beta decay. That is the R process. In the slow process, the beta decay is faster as compared to the neutron capture process. So that is the difference between the R process and the S process. So what is the other opportunity we have? Opportunity to constant the nuclear model in terms of neutron proton asymmetry. For example, like neutron star mass radius, Tiger deformability, log number, moment of inertia, and many. So basically, in the talk, I am going to discuss about this part. So rest of the part, because those who are the people those who are working in the quark electricity or other model, they can also have some more interest on this part. And those who are working on the nuclear reaction process in the astrophysical object, they also have. So many people have many different kind of study. They like to be confirmed by using the predicted data for the GW170817 event. Binary Newton data. So then we start here with a very different model. So it's gonna be like that. So I will not take much time on this because it's a little bit equations and other it's little complex looks. So, but okay. It's a very Van der Waals model. I think you all know about the Van der Waals equation. So, but here it is little bit modified in the form like that way. At zero temperature, if you have no temperature, and the energy density of a infinite nuclear matter, infinite symmetric nuclear matter. So basically, symmetric nuclear matter is the proton density and the neutron density of the system is same, and also they are uniformly distributed. So it is the concept of symmetric nuclear matter. So then the grand canonical example can be obtained from the Van der Waals model by in the expression like E rho. This is the energy density and this is the kinetic energy of the nucleon. So don't confuse with the relativistic ideal Fermi gas of nucleon. Okay, just simple. It is like a nucleon. Okay, and here the rho is the density, and here is the rho is the density. So then another two things is that B and A, these are the two constants in the parameter. That can you can tell two constant which is called parameter. So that means if you see this model has only two constants, two parameters. So basically in the field of theoretical formalism, if a theory contains less parameter and try to predict the more things, then that shows the efficiency of the model. So whatever the model like we have available, like if you are going to Hickle model or semi-classical model or effective model, effective interaction with relativistic, non-relativistic, and other. So each cases, if you see this, the models contain like around 4 to 5 or 6 parameters that fitted with different regions to get the data for the thing. But here we have only two parameters. So we start with the basic. Actually, we are not done. This was done initially started in 2015 by this in 2015 by in this paper published in these two papers, Physical Chemistry and Journal of Physics A, and they started with that. And here is the kinetic energy per term is defined by the gamma 2 by per q, and gamma is a constant there, which is always used in the symmetric nuclear matter is 4. And it is the k is the Fermi momentum, which is connected with the density in a linear relation, and that is rho is the density which is connected with the parameter like this b here. So if you do this and we go for that, and b is, if you see here, b is a constant, but it is only contact with the radius of the sphere. So that means what is the radius you have to take, that we can get. And you can see the more details of this you can say original Van der Waals model, and which is the which is just transform into to obtain the equations for the symmetric nuclear matter. So then this two paper can give you more details of this. And when they're going to do that calculations, and there is a two parameter, one is attractive and repulsive, what I have already mentioned, and they give you the beautiful picture for the nuclear. Then what they have like actually, if they go like this and they put a this and at the saturation density they get like 16 MeV, and the saturation density what I mentioned to you is around 1.6, and there they have the parameter fitted, and this parameter comes like to this value. Then using this value, if you are going to see the relation in previously rho star, that means the maximum density where we can move using the repulsive part of the term. So if you're using that, then max is like almost like it is like the inverse, and we can move up to 1.8. 1.8, that means almost 2 times of the saturation density. But if you know the nuclear neutron star and other, The neutron star is a system where the density is almost like it's more than 4 to 5 times of the saturation density. So that means this model cannot applicable to the neutron star. But still, it is a beautiful concept started by the Van der Waals model by these people, and these two papers they published in 2015 in also book. So next, then another thing here I want to make you more clear how the maximum density we have to reach here. Then there is a quantity we measure in the basically in the nuclear model, because if you remember your basic principle like that, for example, the sound of light, velocity of sound in air and velocity of sound in the metal. Because when I think if you remember of the then you just go to the meter where then you can hear it from the long distance, even the sound. The velocity of sound increase when the density of the system gets increased. So that's why here if you are doing, so what we do here in the model, testing the model, that called the causality test of the model. Causality means, causality is by that, you feel the cause after the effect. If the system, you feel the cause before the effect, that means your causality fails. In a simple way, we can speak like this one. So then we have the square of the velocity here and the density. Then you can see here where the maximum density can go here. It is like 1.8. So it is very less density we can move. So it is not applicable to go for the higher density study. And in the lower density region, we have already constraints for the saturation density, compressibility, kinetic energy. This model also unable to fail. This kind of discussion also we have done in our paper. This paper we have also done. So it failed to explain also most of the saturation properties also. Because saturation property, all the models whatever we have like in the non-relativity, relativity, even also macroscopic, all the models they try to produce this results. But here this model started with very basic things, and it is also more realistic as compared to the models available. But the problem is that it's unable to, and also it is very less parameter, 2 parameter only. So, but its problem is that unable to produce. Then what they did, they modified the term and using the Kamner stirring method. Then what they did, the B basically what is the repulsive part of the term B, which is modified. How they modify? By introducing the new parameter eta, which is connected with the B. That means that is not exactly the new parameter. It is modified parameter of the B. So more technical details you can find in this paper. Okay, these two paper also they published in 2017. Again, because it is a very the process, because even we do not get the predictions, but when we have the modification and we get something result, then it is also going to publish. So more detailed things you can find in here, because I don't want to take too much time for this. But thing is that this is the modification. Then what happened here basically? Here now they get the density reached to the 5.6 more. That means it is enough density for the study of Newton's star. But what is the problem they face? When they go to for it, it is very nice. They get the density. It is very good, good density corresponding to 2.5 times or more. That is also enough for the study of nuclear neutron star matter and other. But the questions arise: how appropriate they have the study proceed, which is the same. So then what happened? If you're going to, I have given one few picture of them. In 2017, they published this paper. It is also in physical review. Then here, if you see, they go for the compressibility. Those who are nuclear people, they know very well one of the physical quantity, because this is the fitting area when they all, because they fit to get the parameter A and B. So here they're going to produce the result. Then when they produce the Van der Waals model, first initially produce the what is the original Van der Waals model, produce the compressibility is around 700, more than 700. Then after this CS that I forgot always the name of these two. Karahan-Stirling method, okay? Then after this method, this is going to produce like 600. It is quite higher as compared to the, because our compressibility region is like this. Maybe it will be like 200 to 240 or to maximum 202 or 260. That is the 220 to 260. We can go like this. So all the things, because these are the different kind of approximation they have taken. In each cases, you can see there is no single one can produce the basic quantity which is called compressibility of a nuclear system. In a nuclear matter system, they are not able to recover. So then this is the thing. Then what is the limitation we get basically? Unable to reproduce the symmetric energy, symmetric properties of the symmetric nuclear matter, high compressibility more than 350, and symmetric energy one of the quantity which is asymmetric nuclear matter. Then that is also symmetric energy. You can see from the coefficient, symmetric energy, asymmetric coefficient in the liquid dome model also. That value is around 28 to 32. Some range band is there. So empirical band is there. So it also produces too high. 32 to 38 is 6, and it is too much difference. And the small difference in the symmetric energy make a great difference in the neutron star and other. So even they do not study anything about compressibility, but sorry. So they do not study about neutron star properties, but the some symmetric nuclear matter properties also not good. So then they introduced new parameters C I have not discussed here, and they also published in this paper in 2018. Then we see this paper, and after that it is also trying to reach, but they still none of the real gas can produce the compressibility. They did not reach to this range. They reduce little bit, but they do not reach to that range. But if this model is fail in the saturation property, so we cannot apply to for the Newton star properties or anything. Then we see this paper and we get interest to do the work. So we come with our basic principle, because as we are familiar with it, I am working in relativistic mean field theory, basically my PhD on that. So in that what happens, we have some coupling constant in the meson field. So coupling constant, we when for more realistic form, we replace this coupling constant by the medium, that means by the density. Everything in a nuclear matter and nucleus come is only for the density plane. So then what is the motivation? Here the motivation to reproduce the symmetric nuclear matter, to constant the symmetric energy coefficient, to validate the causality, because the causality, that velocity of sound exceeds the light velocity of light, that is also one of the things. To Newton star at high density, to examine the model for the binary Newton star model, because at that time we have that information. So it is interesting to see this also. So then to establish this, then we call it GD van der Waals, the density dependent van der Waals model. So what we did here? So in a very simple way, without going to the derivation, I have to tell you, we did only we replace A by arrow and B by zero. That is the two things we do. And after that, all the derivation is going to follow. Your previous first expression for the original model, I show you this 1 minus 0. This is the kinetic part of the nucleon, and this is the arrow. So here my equation is modified. You can see B is modified 0 and A is by modified. And all the derivation corresponding to density and other, you can follow that paper. So it is little complex to do that. And we also, because we followed the papers by the 2017 by this author, then we also tested our density dependent form for all the models, because we have to test that how it is working. So in such cases, this is I can skip this. Here is the pressure, energy, all these things, and here is the compressibility expressions. These are very common, 90, all these things. So then what we get? So after doing this, then we go to this rearrangement. Then what we do? Here the van der Waals model, we can reach up to the density is around 5. So if you see the previous people, to what they did for the first using the extrude volume parameter, then the second one is the Carhan studying method. They reach the density also. Here in two cases also they go to the they cannot reach to the density more like this. But in our case, we reach the density to higher. So here they go up to 5-6 density, but they are unable to reproduce in each case, whatever we discuss, they are unable to reproduce saturation properties and anything. Then after we doing this, then what we have, we reach up to the density 5 times of this, almost 5 times of the saturation density. And this paper, you can see more detailed derivation and everything about that. And about these two work, about more details about the VD, RKS, CS, all the models you can find also in this paper, and also previously I mentioned some of the papers. So here, after that, then also we go for the asymmetric nuclear matter, and we derive for the asymmetric nuclear matter thing, and then we have how the asymmetric matter comes. Asymmetric matter is linked with the neutron proton density difference. Okay, this is very normal. We in most of the paper it is written as alpha. alpha is rho n minus rho p by rho n plus rho p, and so many things. Okay. This is very just technical thing. So then all the after all this derivation, I can do, and we also do for the Newton star. In the Newton star, we have to make the chemical potentials to the balance for the all these things. And here is the expression for the symmetric energy. This is common expression. Everyone knows this. Energy density, second derivative of energy density with respect to the isospin asymmetry. Here is the L coefficient, the first derivative of the symmetric energy, and this is the Fermi momentum related with that, and also a Q-ness parameter, everything you can get. Then what we get? So we get the beautiful result, that is K0 is within the range, which is perfectly come with the range, and we also keep the parameter for AB, not exactly the same what they taken. So we also get the symmetric energy, which is also very perfect, and we also get the L coefficient at the saturation is also very perfect, and we match. These are the constants by many models, so we also match to this, and our results for this saturation is very perfect. Now we have also, we can move up to the higher density like 5. So it is interesting to see the Newton star matter. So it is called as stellar matter. So then we do for stellar matter, this is the energy density expression, this is the pressure density expression, this is the equilibrium, charge chemical equilibrium and charge neutrality you have to maintain. Here we have taken only the electron and muon. So then what we get? So it is the GD model is simple enough because it contains only two parameters, and it is easy to handle the interaction, and it is more realistic because if you have a constant, it is now replaced by the density dependent constant, so it is more realistic in that term we can say, because that is the terminology basically physics use. So it is more realistic when you are depends on the your constant coupling or the strength of the interaction depends on the medium of the interaction. So, and we able to reproduce the saturation property and also causality link extend to this, and which enable to study the Newton star. So now some of the figures. So here we have the figures for the different lines. You can see here the pressure density as a function of density, divided by the ratio of the density of the saturation density. Here K0 is a very good number, and this n is the parameter which is connected with the theory, that is different n values. Okay, so it is the expansion like polynomial type expansion. So how much n you can move? So as it is numerically we solve, so value is not like an integer, it is some number, because we try to constant with this value. So here is the pressure, and here is the stellar equation. You can say for the compressibility K251, K245, and also 243. This is the equation of the stellar matter. That means the Newton star equation of that. And the different bands from the Steiner and Natalia, these are the bands predicted by the nuclear Newton star matter should be. And our three data lying in between the all bands. So it is very beautiful when we produce the data for the equation of state for the Newton star matter. Then we also get the mass and radius of the Newton star. This is the last updated data in 2013. This is the mass of the Newton star is around like 2.01 plus minus something 0.8 or something. Okay, then two solar mass. It also reproduces the solar mass. Here we have given also one of the pictures from MDI. It is also recent paper because I want to discuss, but I feel that the time is not enough for to discuss this paper. So I will also show this graph here. So if you see here, our range of heat for the different parameter and compressibility, I have taken here the symmetric energy at 25 and here also 35. All any data will be come maybe in between that. So that means it is very beautiful to reproduce the Newton star mass also and the radius corresponding. So if you see here, the radius is also around 10 to 11 kilometers. So we get very beautiful picture for that. So then we have the interest to study, to go to the constant, because to see that how our model is constant to the GW events. That is the event what we have discussed, the gravitational wave. So they give the information about the tidal deformability. That is the that is the dimensional tidal deformability lambda. So when we have, then this is the range given by, this is the red color here. This is the range. You can see here, this is the red band the given. Here also this in the blue band you can see. So that means they give a band which the error bar this is there. This is the band, and following the GW event, So if your equation of state is perfect in this, so it must be reached within this band. So here you see for the Van der Waals model, you can see in this paper. So Van der Waals model, we have the all the things will go inside this. It is also very good to because basically when we have the model at the time we have the constant data for the GW. When we fitting the data at the time also we look at the data and we try the model to fit for the all regions. So that's why our results is very nice. So here, so in DM1 and DM2 model, that Gurney and this is the MBI interaction. Here also we try to do that the one fitting that is the one open parameter for the MBI interaction. Here also here the modification happened basically in this paper we have modified the core because there is cost in the Newton star. So the cost equation of state is modified. So critically that is the modification we did here. And here also we get the that is the trajectory between the lambda 1 lambda 2 for the two different because we have a binary system, so two different mass, so they make a trajectory of the lambda 1 lambda 2 tidal deformability for the star 1 and star 2 you can say. So here also you can see this is the line, this line is also LIGO hydro, the experimental people they give. That means if your equation of state is perfect, then you get the range within this. So here also you get very good result. And here also for this MBI interaction will get very good result. That's why the paper published in this journal. So if your model reproduces the data proper way, then it can be have a good publication. So then also we try to do some calculation the moment of inertia. It is going, it is submitted to physics laterally, not at public, which they are again submitted. This is the moment of inertia because if you see some relativistic model, this is the band from the band which is the green band, it is from the LIGO and hydro. And the red line is from the 17 and this 18 is the this line. So most of the things, most of the we are not going to reproduce the data. So that's why in our cases we have very good range for the moment of inertia also. Okay, there is something in the chat. I don't know what. There is less time. So okay, I need another 5 minutes because I will finish. Okay. Okay. Thank you in advance. So this is also one of the correlation we obtained it for the mass 1.4 for the L coefficient, K coefficient, and the Q coefficient. You can find it's very linear fitting. That means our model is very nice to predict all this data of the India model and also Gani. You can see here in this paper. So here also we have taken a correlation for the compressibility, Qness parameter, no, sorry, K parameter, Qness parameter, a mass and a mass of the area. M is defined in one of the quantity is also related with and here is symmetric energy, Qness parameter, comparison K symmetry, L0 is the slope parameter. So here this is the prediction from our GDBDW model, which is submitted to this paper here. So if you see here, our correlation is very strong because all the time we have reached more than the 9.0.98. That means it is very strongly related to the quantity. But if you going to here, this is another paper in 2018 by from for the relativistic and non-relativistic parameter. You can see here in the most of the cases, the correlation is less than 0.5, less than 50%. So if you go into here symmetric energy, they have the relation is very poor. So for the two different mass constant, okay. So here is this one is corresponding to 1.4 constant, our is 4.1 constant. So here they have a very relation, but it is less than 0.6. That means they have a poor correlations, but we get a strong correlation, and that correlation is strong due to because our model is one model, and the parameter is fitted based on the Newton star GW1708 constant. Because these models are previously developed, and they do not have any information about the GW data. That's why it is unable to reproduce the problem because that means we need to change the model in the terminology of this observation. That is the most important. Here is also one of the coefficients for 1.5 solar constant mass, and here also another for 1.6 mass, And here this is the same picture for 1, 2, 3 pictures by that for you can see here. Here all the time they never reach to more than for except 1 or 2 quantities they never reach to 9. But our is always more than the 9.0.98. So very good strong correlation. And that means in case this shows that we have to more because we have to follow the constraint and modify the model to get the prediction because then we can apply our model for the further study and further predict which will be helpful for the also for the experiment. So this is the thing what we have discussed. Develop the density driven and Van der Waals model, and we check the causality, increase the causality, explore the stellar matter, and also we have that mass also reproduced, and we also get the radius is around 11 point. All these things, whatever I saw, these are the things, and we also find a very strong correlation between the established tidal difference in. But there is also many more calculations. But I think that when I prepare the slide, I found that it is already 48 slides. So I need 15 minutes to speak. So I do not add anything more. Okay, thank you. So this all about the discussion. Yeah, this is
Thank
the.
you. Thank you, Dr. Bhuya. It's a nice presentation and nice work also involving density-dependent van der Waals forces. The result that I had seen is actually very nice. So I appeal all the participants, if they have any questions, they can ask.
I have a question. Uh, can you show me the equation of state you have considered?
Okay.
Hello?
Yes.
Equation of state you have considered?
Yes.
Uh,
So here we have like because of for the different many equation of states we have taken. Like for example,
uh,
yeah.
in your calculation, you have considered equation of state.
Yeah, because we have taken a broad range of equation of states corresponding to the minimum value of 25J, started with 236 compressibility, the saturation properties of symmetric energy
Yes.
and compressibility, and also cover up to 35, which is the maximum range of the symmetric energy, and also go to 255, it is almost within the band of the compressibility. Then we try to see that what is the prediction coming for the Newton-Stan merger because that we have taken in the Van der Waals model. And this one I have not discussed much. This was the moment of dependence interaction. This work we done with also we have done in the paper, but we do not have much time to discuss on it.
I want to know the Van der Waals equation of state and the corresponding modification you have introduced in that.
Yes, yes. Because what we do basically normally the modification is very simple. What we have done. So it's very simple. In one line, I can say
Yes.
that we modify the two parameters A and B just by replacing A as a function. And we have to derive all the rest of the things because when you take density, derivation will change too much because it's the all integration everything comes as a function of density. So it is become little complex, but you get the analytic expression also. And if you want to follow this, then you can follow our associate paper. Then there you can find in appendix as well as also we have simplified very perfect.
Actually, I want to know at the boundary you have pressure zero, okay,
Yeah.
and the corresponding density may be zero. So in that case, this energy is infinity. Is it a problem or
Okay.
is it a problem?
Yeah, no, because what we did here, we do not going to for such range because we limit our range with respect to the causality violation expression. So from that, we have to constrain our density with certain region that what can be We do not go to the region where the density is the pressure going to be like a infinity. So that is the
Yes.
technically you have to handle in the in your numerical calculation. That is important. Yeah, true.
Okay.
Okay, thank you very much. Thank you, Professor Bhuya, and thank for all these audience, those are having this attention reading. Okay, I next presenters,
Okay, thank you very
just
much.
Professor
I
Jasmine
thank
Naik.
the organizer
Okay,
again for the invitation and to be here to present my work. Thank you all of the
okay, thank you very much. Thank you, Professor. Uh, welcome, Professor Jasmine Naik. Professor Jasmine. Professor Jasmine, sir, are you present?
Yes, sir. Listening?
Okay, thank you very much.
Okay. It's
Okay, sir.
audible?
Okay, audible, sir.
Audible?
Okay,
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 okay.
sir. So, I welcome to Professor Jasmine Naik. Professor Naik obtained his PhD degree in theoretical physics from Institute of Physics, Bhubaneswar, India. He is now working as a reader of physics in the School of Physics, Sambalpur University, India. His research interest includes nuclear structure and theoretical physics. He has good number of publications in the reputed journals. And welcome Professor Naik to present his presentations. So,
Sir, my
welcome, sir.
PowerPoint is visible?
No, sir, not.
Sir,
Sir, please
not
share it.
visible. I have started sharing. Okay, let me.
Yeah.
Now it is visible?
Present is okay. I got it.
It is visible. You just check whether it is moving or not. Dr.
Okay.
Naik, you just check
Okay, okay.
whether.
Okay. Changing?
Okay. Okay, it's okay. That's okay.
Okay. Okay, so very good morning to everybody. First of all, I want to like thanks to the organizer for giving me a chance to present my work. Okay. So my today's topic is high spin structure. Wait a minute. No. Okay, so today my topic is high spin structure of chromium and nickel isotopes near Z is equal to N line with PHF model. So my basic outline are introduction, where I will give detail the introduction basic structure physics for the beginner. Then I will go briefly I discuss PHF model. Then I will discuss result discussion, where I will discuss about chromium result and nickel result. Then I will go to my conclusion. So let us start with the very basic things. So let us start with the chart of the nuclei. So if you see, this is a standard chart of nuclei. This chart of nuclei tells that if you see there are around we have around 300 nucleon we have so far experimentally studied, and out of this only few are stable. You can see this black line, a black dot, these are the stable nuclei, and this blue line which are we have experimentally observed, and this is around 3000 nuclei. Until we have lot of nuclei, we have to explore both experimentally, because this is a theoretically predicted that this number of nuclei has to be exist, or you can you can predict in the laboratory in future. Okay, so this is standard. Then come to the high spin nuclear physics. I will discuss high spin structure. So let us give little brief discussion about the high spin structure. So here what will happen, this is my target nucleus and this is my projectile. When the projectile we bombard with the target nucleus, initially this target nucleus is rigid. They do not do any rotation or vibration. These are basically rigid constant. So when you bombard with this electron with some energy, as soon as you touch this nucleus, you start rotating. And this is in the time scale. This is happening in the time around 10 to the minus 22nd. And rotation is at the beginning. The rotation is 0, and I start as soon as it interact with this, it start to rotate because this energy of the nucleon is transferred to the nucleus. At the beginning, because of the energy, this is a very high temperature. Beginning some pure proton, neutron, alpha particle, they come out from the compound nucleus, and this make this nucleus to cool down, and this is happen on the around 10 to the minus 10 the minus 19 second. By this time, the nucleus is rotating, very slowly rotating. That is around 10 to 100 rotation it has completed by that time. Okay. And then after it cool down, it is then it produces different gamma ray, and by that time it is very fast rotate. You can see the 10 to the power minus 5 to 10 to the minus 10 rotation it will take by that time. After decaying gamma ray, it will come down to the ground state, and by that again is rigid and stop there. So what will happen? Normally, if you see this graph, if you plot excitation energy versus angular momentum, and then in this nucleus is produced somewhere here. This is a temperature, high temperature. So here it will do some particular excitation, then come down to this region. Here by gamma decay, it will slowly decay gamma and come down to the ground state, where there is no angular momentum or it is only constant. Okay. So one more figure I will just show you. So here you can see that nucleus has a different type of motion. So it is showing that here it is blue dot represent proton or neutron, and the rotation, this rotation around the nucleus, that is showing the single particle rotation, and this whole nucleus rotating like this, it is representing the collective rotation. So this happen as soon as you interact with the external member, it will rotate, and after gamma decay, it will come and stop basically. So you can see what is the collective rotation and a single particle rotation. Okay, so if you see that in nuclear physics, only deformed nucleus can give collective rotation or collective vibration. Normally, spherical case, the single particle rotation and this collective rotation we distinguish. So, normally, you have to consider this all are collective rotation. Sorry, all are single particle rotation. So, these magic number are special in nuclear physics, and all nuclei having magic number are spherical in nature. So we go away from the magicity, deformation increases, and it is maximum deform at mid cell. Again, if we increase the number of particle filling orbit, again it will become decrease the deformation, and again when you come to the spherical cell closure, that become again spherical. And only that I have told you, again, deformed nucleus can rotate or vibrate. A spherical nucleus we cannot distinguish. So because of symmetry, we can consider only single particle rotation. And again, this rotation and vibration are single particle as well as collective rotation. And because of this, again, single particle collective, we mix all this together, and large number of nuclear phenomena we can see in nuclear physics. Okay. So by now, if you see, then we have a lot of stable beam, a lot of external setup are there in India as well as abroad. A lot of good electronic facilities are there, detector are available there. So with this rich electronic setup, we can study nucleus up to very high spin as well as very high energy ratio, as well as high temperature. We can study all those things. We can study. So let us have a look. What are the different gamma? This is high spin phenomena. We can see in our nuclear physics. We can see. So if you see the Rast line, then you can have this is super deformed structure where we can study this. And this is polar to oblate transition. We can see. Okay, this is magnetic rotation. This is hyperdeformed. A lot of phenomena in there. This is backbending phenomena are there. So out of this, we can in around 50 mass region, I will discuss some of this. We support different have and have different structure, bend transmission and back bending. Okay, it's a state double back bending, isomer, oblate state and set resistance, and many more are there. So let us discuss some of this. What are they exactly? Let us discuss. So let us first show me what is a deformation, beta deformation of control moment. So if you see there's a nucleus, you have you can define beta in our calculation. Beta is nothing but your this is a radius. If you can consider 3D structure this or this. If you see this, in this case, what will happen? You can consider this axis is symmetry axis. In this case, you consider this is symmetry axis, and in this case, or you can consider A and B each less than C. In this case, A and B is greater than C. So in this case, your del R is in negative. In this case, del R is positive. So this structure we can call polate. This structure we can call oblate structure. And we can see this potential energy surface calculation. Then this is you can potential surface energy. And then with energy, if we change the beta, then the nucleus show different energy, and the lowest energy you can consider nucleus is a deform. Okay, and different region, different type of nucleus are there. So if you can see this, in this case, this is spherical because beta is equal to 0, the minima is there. Here it is spherical. If you see here, the -2 beta gives me the lowest energy. So this is oblate. See this prolate. So in this way, you can see this different energy prolate or oblate from energy total energy system. We can step whether where is minimum in beta negative side or positive side or 0. And similarly, if you combine two bend, and then we can get a crossing, then we can get a back bending. And this when two bend cross, basically the ground bend and S bend, next side bend cross, then we can get this type of you can call back bending. If not cross, then you can get a bending. Okay, so let us similarly there is different quantum mechanical transmission require magnetic pole require to decay from one state to other state. Because of this, sometimes what happens, some state stay beyond 10 to the minus 9 seconds, and then it is called isomer. Okay, normally what will happen, all state decay to the ground state by 10 to the power minus 12 seconds. Okay, I have so for the beginning. So when you bombard, we take this is 0, then everything will happen within 10 to the power 12 seconds, or some cases because of the quantum fluctuation or quantum this selection rule, some state stay beyond 10 to the power minus 9 seconds, and that is called isomer. Okay. So this is heteroform formalism. I will not discuss this. This is schematic diagram for heteroform formalism. Okay, so we start with the heteroform, then we can construct the engineering state, then we can do angular moment projection to get the structure. And this is the different equation used for this. So I am not discussing. If you want, you can see this later. Okay, and the calculation, when we do the calculation, we can declare a core, because if you took 0 core, then you require large number of nucleon you have to consider. Because of this, what will happen, your model space is very high and become problem for calculation. That's why we take a core, and above this we can consider this calculation. So in this case, I have taken calcium 40 as my core, and I have taken the rest of the nucleon above the core, and I have to perform the calculation. And this is a single particle energy, orbit energy for the calculation. In this case, I have to consider this P3 by 2 is equal to 0. Normal is to 0, because for calculation do not depend exactly how much your exact energy, only take care on relative energy. So we have to consider this equal to 0 and perform calculation. So these are the, some of the information available for experimentally for we get. So you can, I have considered nickel 56, which is a lifetime maybe only 6 days, and I have taken chromium 50 and 52, which are stable nucleus. Okay. So if you say again, this is alert may go to the Hartree-Fock orbit, then I will discuss little bit result. So this is the result where I have performed Hartree-Fock calculation and get the orbit ordering. This is for oblate. You can oblate. You can see this is a higher JR lower, and in prolate you can see the higher small JR lower. So by including different orbit, we can see that which integer configuration nucleus is nucleus are in, and we study the produce projection. So this is the experimental result. High spin structure for this is chromium 52, and this is my theoretical calculation. So you can see this angular moment projection. You can get up to, you can get up to this is a 8, 10, 12, and theoretically you can get up to 14, and this is a sideband which is get up to 16, and you can get up to 13 experimentally. So so you can see this, if you see this, when you do the abnormal projection for polate and oblate state, initially your polate state is going this, then basically this is spin versus energy. So after a certain time, what we will find that these both polate and oblate are nearby. We can show that these are the shape coexistence. So here we will see that this is polate is going like this, and oblate, when you perform angular moment projection for oblate state, again this is cross, and this gives me the shape coexistence. And if you take k is equal to a high k band, then you can get that. Okay, so here is little bit the symbol. There's some mistake in the symbol, but anyway, this is high k band, k is equal to this is corresponding to this, and this is oblate band, and this is, you can say this is lower in energy compared to the ground state as well as oblate. So in this cannot decay directly to this band. So this lifetime is more than your nanosecond. This is equal isomeric state. Okay. So you can experimentally you can see this theoretical and experimental observation are very good. So this is experimental state, and this is theoretical ground band. Now this K band is lower than this, so that's why it cannot decay directly to this. It require high K and high L, high higher order of electric and magnetic moment to decay this. So that's why become this is isomer. Okay. Similarly, I have option for 52, 52, and this is a second back bending. So you can have also get theoretically as well as experimentally, you can have both second back bending. Fast back bending is like this here, then go upward, again go back. So this is a double back bending you can call. Both 52 and 50, both experimentally and theoretically you can get back bending, which is this PHF model explained properly. And these are B2 value. I'm not discussing this. Again, come to the nickel 56. If you're nickel 56, we have performed partial calculation, and we can get, this is the, you know that nickel 56 is 28 proton to neutron, and both are isomer as a cell closure. So the ground state is spherical, the spherical bit 0 minimum. But if you do the constant calculation, then you can get this is normal deformation. We can get some deformation here. You can get some deformation here in both sides, polate and oblate side. You can get deformation. So that means if you increase the constant calculation, then you can get a deformation nucleus. But ground state is spherical or low deform. So if you see this in normal deform, we can have little ordering as proper ordering. We can fill up to F7/2 orbit, and there's you can get cell closure, and this is a cell gap of the 28 cell gap. So you can see. But if you can consider increase the deformation by using constant calculation, so that you can this orbit you can see this half orbit, which is coming from P3 half, we occupy, and we can get a hole in F7 half. You can see that, you can see this F7 half has gone up. We can get in super from one step, we can get two proton hole, two neutron hole in your F7 half. You again further do the calculation, we can get four particle, this 5 half and 7 half become empty. That means we can have 4 hole in your F7 both in proton and neutrons. Basically, we have 8. Okay. So because of this, we have performed a calculation. This is the normal deform. This is the deform 1. This is deform 2 calculation. We have performed, and this is. So this is deformation. We have calculated the experimental theoretical, and this is two super deform band hedge observed. So you can see this super deform 2 solution very well. This new configuration very well. This normal deform are basically not that not collective nature. These are, you can see that they are not smooth. You can see this smoothness, and this is not smooth. They are not collective. These are collective. Okay. Okay. With this, I conclude my work. So basically, PHF model, using PHF model, we have studied super deform band and hyperdeform band, and band transmission. We can have a band transmission study. We can also calculate the electromagnetic properties of band, but I have not given. I have discussed a little bit about that. You can here. I can show you. I can give an band different B2. These are other electromagnetic properties, which you can also we can calculate in PHM model. Also, this is same as your agreement experimental, or as your cell model calculation. Okay. So with this, I want to say that this is basically PHM model is a very good and a successful in explaining experimental observed different properties, as well as is able to cover to explain all the future work. Okay, thank you.
Thank you, sir. Thank you, Professor Jamil. I request all the audience, if you have any brief questions, please. Hello, audience.
I
Okay,
think
sir.
I think no question. Okay, sir.
Okay, sir. Thank you very much. Thank you once
Okay,
again. Now, next, I request Professor Rudranana Sahu.
Yes,
Dr. Rudranana Sahu has
to
completed his postgraduate from Sambalpur University, Odisha, and had successfully completed his PhD from IIT Raipur, Punjab, India. His research area is experimental neural physics. He has a good number of scientific publications in the field of neural physics in the international and national level of reviewed journal and conference. So I request Professor Sahu to present your presentation. Please, sir.
my slides are visible.
No, sir. Till now, we are not getting.
Okay, I am sharing.
Share the screen, sir.
Okay, I am sharing. Now it's visible?
No, sir. Not yet.
Not yet?
Not yet.
Okay. Let's see. Hello?
Yes, sir. Yes.
It is visible?
No, sir. So click on these three buttons nearby the share. You click on the near buttons. Sorry, share. Click on the share. Okay, sir.
Okay.
Then click on the screen.
Okay, wait a minute. I'm doing.
I think it will be.
Yes, now it is visible?
Yeah. Look, now it is okay, sir.
Now it is okay. Slides are moving, right?
Yes, yes, sir.
Okay, okay. Thank you for your introduction, and I am very much thankful to the organizing committee for giving this chance to present my work. Uh, the title of my talk is the effect of neutron transfer in subbarrel fusion enhancement, and the talk is organized in the following manner. First, I will tell about the nuclear reaction. Then I will come to the subbarrel fusion. Then outstanding issue in subbarrel fusion. To understand the outstanding issue, we perform some experiment at Inter-University Accelerator Center. They're taking the 3537 chlorine plus 130 tellurium. I will tell about this. And finally, I will conclude my talk with result and discussion. First, nuclear reaction. Nuclear reaction is a process where two nuclei interact with each other and mass, charge, and energy exchange between them. And sometimes the new element is formed. And the nuclear reactions are represented are like this: A plus X equal to Y plus B, and there is a extract of Q. Q is called energy kinematics of a reaction, and it is nothing but the mass difference between the incident channel and exit channel. A plus X is called incident channel, and Y plus B is called exit channel. And if we multiply with this mass difference with C square, then we will get the dimension of energy. And in generally in the nuclear experimental nuclear lab, what we did, we actually placed a thin tellurium target and thin target, very thin target, and we bombarded projectile beams from an accelerator. And when we bombarded, after the interaction of projectile and the target, then in the outgoing channel, we are getting some particle at some angle. And when we measure the particle based on, we measure the desired particle based on our physics motivation, on the basis of which we are performing the experiment. Accordingly, we measure the particle. And this is here I am actually briefly explaining the different kind of nuclear reaction. According to the structure of nucleus, nuclear reactions are classified as the direct nuclear reaction and the compound nuclear reaction. Direct nuclear reactions are the elastic scattering, inelastic scattering, and transfer reaction. And transfer is further classified as the pickup reaction and stripping reaction. In pickup reaction, when projectile comes towards the target, it takes some nucleons from the target. However, in the stripping reaction, projectile gives some nucleons to the target. And there are also charge exchange reaction, that means a proton is exchanged between the projectile and target. And also breakup fusion. When projectile comes towards the target, it gives a part to the target nucleus, that is called the breakup fusion reaction. Direct nuclear reactions are mainly studied to understand the reaction dynamics, evolution of reaction dynamics from deep elastic collision to the quasi-elastic collision. And the compound nuclear reaction. Compound nuclear reactions are studied to understand the static and dynamical properties of nucleus, and these are classified as the fusion-fission reaction. And when we are providing much more energy as compared to the barrier, barrier is nothing but, since we are dealing with the nuclei, then nuclei are actually highly positively charged. That's why there is a Coulomb repulsion between them. And when we are providing much more energy as compared to the Coulomb barrier, the fusion-fission reaction is more probable. And when we are providing just above when we are providing just above the barrier, energy providing just above the barrier, that is called above barrier fusion. And subbarrier fusion is that where we are providing less energy as compared to the barrier, at that time also fusion happens. That is actually interesting, because although we have less energy as compared to the barrier, fusion takes place. This is my area of interest and area of interest. This is the schematic representation of the nuclear reaction. This is our target nuclei. This is I am showing here one target nucleus, and this is a projectile. And at a different interaction, different kind of nuclear reactions occur. And you can see when the head-on collision occurred between the projectile and target is completely fused, and the completely fused and compound nucleus is formed. However, in case of in peripheral region, if the interaction occurred, then the some nucleons as well as energy transfer between the projectile and target, and that leads to the direct nuclear reaction. Since my area of interest is the subbarrier fusion, First, I will explain how fusion occurs. When projectiles comes towards the targets with slightly much more energy, it completely fuses with the target. And when it completely fuses with the target, all the energy, all the kinetic energy of the target projectile actually dissipated inside the target nucleus. And that's why since the nuclei are many-body quantum mechanical system, the repetitive interaction occurred between the projectile and target internuclear 90 degrees of freedom, and finally lead to a thermally equilibrated compound nucleus. And that thermally equilibrated compound nucleus comes to ground state by emitting alpha particle and the proton and the neutron. When the excited nucleus don't have much more energy to emit particle, at that time it emits the gamma ray. And in this case, in the nuclear reaction, the most physical observable quantity is the cross section. And since we are providing some projectile to the targets, and there is some interaction, and how many how many projectiles is actually interacting to the target nucleus in the thin foil. Taking this, we can calculate the cross section. In principle, by counting the number of gamma ray or proton or the alpha, any one of the particle, we can calculate the cross section. And directly we can also measure the number of evaporation residue, and we can calculate the fusion cross section. I am interested, subarray fusion has the possibility to explore the static and dynamical properties of nucleus. It provides a scope to go far from the nuclear stability belt. It helps to create the super heavy nuclei with longer lifetime because it has probability low excitation energy. And it also helps to understand the astrophysical process like energy production in star. It gives an idea about the internuclear potential landscape, and has probability to explore new reaction dynamics in the low incident energy. And as per the literature and the present understanding, the subarray fusion occurs due to the effect of tunneling, and mainly due to the effect of tunneling. And the tunneling probability. Hello, am I audible? Okay. Effect of tunneling. The subarray fusion mainly occurs due to the effect of tunneling, and the tunneling probability is further modified by the static deformation, collective excitation, and positive q-value neutron transfer channel. And effect of tunneling is well known to everybody because tunneling is a quantum mechanical process where a quantum mechanical particle passes through a barrier, although it has less energy as compared to that barrier. Since in our cases the nuclei are the quantum mechanical particle, the tunneling comes automatically. And I will explain static deformation, collective excitation, and frequency channel one by one. And you can see here static deformation. When we are actually considering the nuclei may all the nuclei are the nature except few are nuclei are in the nature are not always in spherical in nature. Some are in the prolate and some are in the oblate. And since the distance between the projectile and target is modified due to their deformation intrinsic properties, the Coulomb barrier between them also modified. Due to the Coulomb barrier modified, the fusion probability also get modified. You can see here one example: samarium 144, samarium 148, and samarium 158. The deformation is gradually increasing, and this is our projectile, obscenely projectile. Since the deformation is gradually increasing, our fusion cross section is actually enhancing in the below barrier, but in the above barrier you can see from one here, this is normalized. The energy is normalized with the barrier, and the cross section is normalized with the geometrical cross section. In the below barrier, actually our cross section is enhancing due to the static deformation. In the above barrier, the cross sections are actually following the same line. If you also come to the collective excitation, due to collective excitation, when projectile and targets comes towards each other, due to the wave interaction as well as the external stress, the both nuclei actually collectively excite. Due to the collective excitation, the different rotational and vibrational states of the projectile and targets are automatically evolved. That also modified the barrier between the projectile and target, and that also modify the fusion cross section. You can see here, this is for titanium 48 and ferrum 58. When 2 plus and 3 minus state is coupled with this calculation, then our barrier is reduced to 3. The barrier is reduced as compared to one dimensional barrier. Since the barrier is reducing slightly, then our fusion cross section is significantly enhancing. The static deformation and collective excitations are the intrinsic properties of the since the static deformation and collective excitations are the intrinsic properties of the interacting partner. These two factors come automatically. But the positive Q value neutron transfer channel has some peculiarity because why it is taken into account as a factor. It is taken into account as a factor because you can see here in this schematic picture, when projectiles comes towards the target, then since neutrons are the insensitive to the Coulomb barrier, neutrons try to interact between the projectile and target. And when it try to interact between the projectile and target, exchange between the projectile and target, then there is a bond formed between the projectile and target by the neutrons. And that bond actually sometimes trap the projectile towards the target, and sometimes it escape due to the positive Q value. The Q value of the reaction is positive, then it also helps to rearrange the nucleons in the this is highly uh, thermally equilibrated compound nucleus, and again it is comes to the same process. You can see here the fusion cross section of the calcium and tin systems systems measured. You can see in calcium 40 and SN132 we have 5 positive Q value neutron transfer channel, but in this case 132 we don't have any positive Q value neutron transfer channel. Since here we have 5 positive Q value neutron transfer channel, our cross section is significantly enhanced in the below barrier. However, in the above barrier the cross section are actually match uh, falling one upon another. And here we are comparing the fusion excitation to fusion cross section of the both system by normalizing the cross section with the geometrical cross section and the incident energy with the barrier, such that to reduce the radius effect as well as the barrier effect, we actually then you can see this similar kind of observation you can see also in the calcium 40 and SN124 and in this case. However, if you see in this system, here also excitation function of the sixth system is compared. You can see here also we actually normalize the measured cross section with the geometrical cross section and energy with the respective barrier. You can see in tellurium 130 and nickel 58, we have tellurium 130 and nickel 58, we have 11 positive Q value neutron transfer channel, and in case of tellurium 130 and nickel 64, we don't have any neutron transfer channel with positive Q value. Although there is difference of 10 positive Q value neutron transfer channel, the fusion cross section is fusion excitation of both the system is following the same line. However, if you come to the calcium case, the fusion excitation functions are splitting in the below barrier. However in the above barrier, both are actually matching the above barrier. That signifies that whether positive Q value neutron transfer channel is really effective towards subarray fusion or not, this is not to us, because in the earlier observation we saw the positive Q value neutron transfer channels has effective towards the subarray fusion, but in here we saw that the some of the cases the positive Q value neutron transfer channel remains silent, there is no effect, and this PQNT channel effect is first observed in the nickel system. You can see here nickel 64, nickel 64, nickel 50, nickel 58. In this case, we don't have any positive Q value neutron transfer channel, but nickel 58 and nickel 64, we have two neutron transfer channel having positive Q value. That's why the cross section of this system is significantly enhanced as compared to the nickel 64 and nickel 64 and nickel 58. And one more interesting thing in the subbarrier fusion is that coupled channel calculation will predicts the fusion excitation function at extremely below barrier. However, if you went down to the 7% or 8% below barrier, uh, then at that condition, our measured fusion excitation function actually sharply fall as compared to the theoretical prediction, and sometimes it got enhanced as compared to theoretical prediction. And this reason is not known to us. The questions in the subbarrier fusion is that if I will summarize the question, the problems in the subbarrier fusion is that the effect of positive Q value neutron transfer channels towards subbarrier fusion enhancement is not known to us. If positive Q value neutron transfer channel is really effective toward the subbarrier fusion enhancement, then up to how many neutron transfer channel is really effective? And the behavior of fusion excitation function is not known at extremely below barrier, below 6 to 7% below barrier. To understand this problem, we perform an experiment at Inter-University Accelerator Center, taking 35-37 chlorine plus 130 tellurium as system. And you can see we choose these two systems because in the 35 chlorine case, we have 6 positive Q value neutron transport channel. However, in case of 37 chlorine, we don't have any positive Q value neutron transport channel. And if we will see 35 chlorine case, the outermost valence shell of neutron is half filled. However, in case of 37 chlorine, the outermost valence shell is full filled. Due to this reason, we choose these two system and we perform the experiment. We try to measure the fusion excitation, fusion cross section from 10% below barrier to the 15% above barrier. This is our experimental setup. This is the one of the unique setup present in India. This is called heavy ion reaction analyzer present at IUC. Here actually you can see this is our target chamber where this is our target chamber, this is our focal plane. And you can see before going to the total setup, first I will explain how the target chamber works during the experiment. You can see here this is the incoming beam direction and this is the target ladder. Here we fix 2 target and 1 quartz crystal. Quartz crystal is present here to focus the beam, whether the beam is properly focusing or not. And we also fix 2 target here. And here we have 2 monitor detector, to monitor the beam as well as to get the normalized cross section. And this is our target chamber and setting of the target chamber. And after the reaction, when actually beam falls on the target, then actually in the outgoing channel we have enormous and many particles with different kind of reaction mechanism. But this is heavy ion reaction analyzer has the capacity to select a desired particle, which particle you want according to the your physics motivation, and it transferred from target chamber to the focal plane. Based on the selected particle, you can apply the electric and magnetic field to the electric dipole and magnetic dipole moment and Q3, Q4, such that it will transfer the particle from target chamber to the focal plane. And the most beautiful thing of this setup is that it transports the particle from target chamber to the focal plane without losing its energy. And in the focal plane, we placed one multi-wire proportional counter. It is nothing but a gas detector, and in that gas detector, we actually measure the evaporation residue. But in our cases, the desired particle are the evaporation residue, because after the reaction, I already told that when the thermally equilibrated compound nucleus emit a gamma ray and alpha and proton, the reaction residue is called the evaporation residue. And here we actually transport the evaporation residue from target chamber to the focal plane without losing energy. You can see this is the setup of our heavy ion reaction analyzer. Here is our target chamber, here is our focal plane. You can see then question is that how actually we measure the evaporation residue. You can see we know the recoil energy of the particle. After the reaction, we can calculate the recoil energy of the particle using this formula. This is 25 for our case, around the barrier is 25 MeV, and we can also, since we calculate the recoil energy, we can calculate the time of flight. And we can calculate the charge state of the evaporation residue using this formula. And since we have the energy and the charge state, then according to the energy and charge state, we can provide the electric and magnetic field to the Q3, the different elements of the heavy ion reaction analyzer. And since we have the energy in recoil energy, then we can calculate the energy loss of the recoil residue at focal plane, and we have the time of flight. And by making a coincidence get between the time of flight and recoil energy, actually we measure the evaporation residue. You can see here we actually measure the this is for the 35 chlorine plus 130 tellurium. You can see it is just above the barrier. It is 6-7% below the barrier, and it is 10% below the barrier. When we are going down to the barrier, at that condition the evaporation residue are actually gradually decreasing, and the beam-like particles are increasing. You can see here we have only 8 evaporation residue, and interestingly, these 8 particles are evaporation residue or not. This is very difficult to actually visualize. If this is actually are not evaporation residue, then our experiment will be there is some fault in the experiment. That's why what we did to confirm these are actually evaporation residue or not, we actually removed the target from the beam line. We only projected the beam to the heavy ion reaction analyzer. However, we could not able to get any particle within this gate. And as I told you, this is the energy loss and the timing information. And we didn't get any particle. That's why you confirm that these 8 particles are the evaporation residue. And so far we calculate the evaporation residue for these two systems, and you can see the spectrum. And after that we calculate the cross section using this formula. This formula is just this is the fusion cross section formula. We can actually derive this formula from the general cross section calculation formula. We have the evaporation residue. This is the efficiency. Efficiency of the HIRA is calculated easily because it is efficiency is nothing but if we have 100 particles are producing in the target chamber, all the particles are not going to the focal point. That's why the efficiency factor is taken into account. And YER is our evaporation residue within that gate. And YM is the monitor yield because we have two monitor detectors, and this is the other focus section. And you can see we calculate the fusion cross section of the both the system. You can see here we actually measure the cross section from this is for 35 chlorine case. Here we the lowest measure cross section is 0.03 millibar, but here we went from 1 microbar to the 650 millibar. We measured up to 6 order of cross section, and this kind of experiment is only performed in the nuclear physics experiment, and you cannot get this kind of perform experiment in other field of physics. And since our motive is to understand whether positive q value neutron transport channel is really effective toward the subarray fusion or not, then what we did, we actually actually compared the fusion excitation function of the both the system by normalizing energy with the barrier and fusion cross section with the sorry, we actually measure the compare the both the fusion excitation function by normalizing energy with the barrier and fusion cross section with the geometrical cross section. After normalizing, you can see the fusion excitation function is splitting in the below barrier. That signifies that the positive q value neutron transport channel has some effect toward the subbarrier fusion. And after that, we also did the theoretical calculation and using CC full code, and it has capacity to calculate the cross section using one-dimensional barrier penetration. It takes the coupling of inelastic excitation into account. It also add two neutron transport channel to the calculation. Two neutron transport channel cross section to the calculation. You can see since in the 37 chlorine we don't have any positive q value neutron transport channel. First we tried to actually reproduce the experimental data with the theoretical code. When we actually did, then it is actually well reproduced at the below barrier as well as the above barrier. And however, in the similar footing, when we did the calculation for 35 chlorine case, actually it reproduced the cross section down to 6% below, down to 5.6% below barrier, and below that after that it is not reproducing. And when we actually added two neutron transport channel to the calculation, and it is actually reproduced the fusion cross section, measured fusion cross section. And that also signifies that from theoretical calculation, that also signifies that the two neutron transport channel, that is neutron transport channels, are actually one of the important factor to enhance the fusion cross section at extremely below barrier. And since we measured the fusion cross section of this 37 chlorine up to 1 microbar cross section, actually we also did the barrier distribution calculation, astrophysical S factor calculation, as well as the logarithmic derivative calculation. You can see this is the barrier due to one-dimensional barrier penetration model, and when we are actually adding the coupling to this calculation, then this is the experimental data. You can see the barrier is actually reducing to two parts, broadly actually reducing to two parts, and the total barrier is reducing. And to understand the behavior of fusion excitation function are extremely below barrier, what we did, we did the astrophysical S factor calculation. And when actually we are actually going down toward the energy, then our S factor is actually increasing. And that signifies that there is no fusion hindrance for our system for 37 chlorine case. And to see the effect more clearly, we also did the derivative of S factor, that is called factor calculation. And at that condition also, when the energy is decreasing, our LE factor is actually gradually increasing. That signifies that we don't have any fusion hindrance for 37 chlorine gas. Maybe when we will measure the fusion excitation function down to 10 or 12% below barrier, then at that condition, then we may get the fusion hindrance. But this up to now, we don't have any fusion hindrance. And since we measured the fusion cross section of this 37 chlorine and 130 tellurium, we also compared our data with the other measured data with same projectile 37 chlorine case. Here also 35 chlorine case. You can see here we went down to 4%, 4 order of magnitude as compared to the other measurement. Here we also went one order of magnitude down as compared to the other measurement. Here one most important thing is that in this case 35 chlorine and 24 magnesium case, you can see the fusion excitation function is significantly enhancing, and that may be due to the positive q, that may be due to the q value of the reaction. And from this study it is known that not only positive q value neutron transfer channel is effective for the subbarrier fusion, but reaction q value also plays a crucial role to understand to for the subbarrier fusion enhancement. In summary, I will say we measured the fusion cross section of the 35-37 chlorine from 10% below to the 15% above barrier, and for 35 chlorine case system we found that the fusion excitation function is significantly enhanced as compared to 37 chlorine case, and the effect of positive q value neutron transfer channel has been observed and emphasized in the couple channel calculation, that is the theoretical calculation. And we didn't get any fusion hindrance down to 10% below barrier for this 37 chlorine case. Thank you. Hello. 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 Am I audible?
Yes, sir. Yes, yes, sir.
Actually, I have completed. I am looking for the question.
Okay. Okay, let's for the question. Please, some students may ask some question. Already have some question, please ask.
Okay, then I think nobody have any question. I am stop sharing,
I
right?
think. Yes.
Oh,
Okay, okay. Thank you.
okay.
Hello. Hello. Hello, Professor Vishwa.
Yes, yes, I'm here.
Okay. Welcome, Professor Vishwa.
Oh, sorry, I am not
Uh,
noticed.
okay, okay. So, respected Professor Subrat Kumar Vishwa has completed his PhD from Institute of Physics, Bhubaneswar, Odisha. His research area includes study of the finite nuclear structure and the neuron star physics. Mostly, he worked on this equation of the state of the neutron star. Currently, he is working as a postdoctoral fellow in German University, China, in the Department of Astronomy and Physics. He has a good number of research publications in the field of research in the different reputed journals and conferences. And present the different topic in the different platforms. Welcome, sir. Welcome, Professor Vishwa. Please share your slide and present, sir.
Okay. Thank you. Thank you for the introduction. Can you see my slide? Hello?
Yes, sir. Yes. Yes, sir.
Okay. Okay. So, welcome to everybody. So, my topic is effect of high meson on the equation of state of hyperon star. So, myself, Dr. Subrat Biswal, and now I'm working in Department of Astronomy, Xiamen University, China. So, plan of my talk is as follow. So, I will give a brief introduction. It's clear to you, sir? Hello?
Yes, no problem.
Okay.
Visible, clearly visible.
Okay. So, plan of my talk is as follow. I will start some brief introduction about Newton, and I will discuss about why Newton star is so important in nuclear physics and astrophysics, and then I will talk about some technical mathematical formulation of theoretical formalism, and then I will discuss the hyperon puzzle and why we study the hyperon star and what is the implication in nuclear physics. Then we show some calculation of calculation with various parameter set and some of my research published, and then I will talk about the result discussion, and finally I will summarize it. So question is that when you talk about the Newton star, then the first question comes to your mind that what is the Newton star? Why it is so important for nuclear and astrophysicists? So Newton star is a very dense star having maximum amount of neutron. So it does not mean that it's all have neutrons. It's have proton and electron also. Other particles are there. There is a very the internal structure of Newton star is very complicated, and it's not very clearly understood also. So Newton star are formed when a massive star runs out of fuel and collapse under gravity. Suppose here So here consider suppose this is a star. So inside the star, the nuclear fusion reaction happens. So it means the hydrogen combined with helium and some amount of energy. This and so on and so forth. The reaction continue up to the heavy element like iron. After iron, this reaction became endothermic. The energy will not come out of from that reaction. So but it will take the energy from the environment. So after iron, we cannot possible to go by this nuclear fusion reaction. So nuclear fusion reaction give a outward pressure, and which is balanced by the gravity of the Newton star, because Newton star is a dense object. So its gravity pull inward, and the fusion reaction energy that gives outside. So there is a hydrostatic equilibrium between these two force, and the star exists. But when the nuclear fusion reaction up to after it formation of iron, then the fusion reaction process to endothermic, and it will stop. When it stop, then the gravity pulls the star inward, so it is goes a supernova explosion, the type 2 supernova explosion. Then the maximum part will be broke, and only few the central part, which is the core part of the star, will remain, and that will form a Newton star. Then the next question comes to our mind: when every star after the core collapse became a Newton star? Simply answer is no. It depends upon the original mass of the star. There is just two possibility: one is a small star and it is a large star. If it's a small star, then it goes to the final stage, a white dwarf. And if it is a large star, then it will be two type possibilities there. One is the Newton star. If the star initial mass is very high, then it will go to a black hole. So why then how Newton star exists? Still After the core collapse, also when the core part is formed, the neutron star is formed, still gravity is there, but then the gravity pull inwards, still the gravity is pulling inwards and gives the necessary outward pressure. This is the question. So the necessary pressure given by the degenerate pressure of the fermions, because the nucleons like proton and the neutrons, they are fermions, and you know that if when suppose a degenerate gas, then all the energy levels are filled with one upspin and downspin particles. If you compress these systems, then the other particle will try to come inside these levels, but they will not allow because of the Pauli explosion principle. They give a pressure, and this give a degenerate pressure, and some part of that outward pressure is given by the degenerate pressure, but it is not sufficient to hold the gravity. So that's why the nuclear force also play important role. When the two nucleons come very close to each other, you know that this is the nuclear potential graph, and at very short distance, the nuclear potential became repulsive. And these two gives the necessary outward pressure to counterbalance the gravity, which pulling inward. Then then I will then this is a systematical graph of the internal structure of the neutron star. So you can see that it's just like a onion. So if you open up the leaves of the onion, you will find the density will increases, and similarly here if you go from outside to inside, you will find the neutron star's density goes on increasing. With the increase of density, the new particles with new degrees of freedom or new particles will come out. And if you see here, the upper surface part will contains the most of the clusterization of nucleons, which make the nuclei like iron, silicon, and all those things. And if you go inside, then the extreme density, the collapse the nuclear structure, and it became the nucleons, electrons, neutron, proton, something like that. They are freely moving. Then if you go to deeper, then you will find the quarks are there. And if you you also find some level where the nucleons become the hyperons, and we will discuss how they become the hyperons. And so if you consider the whole things are the incompressible fluid of the nucleons, then it is a nucleon star or neutron star. And if you call this some amount of hyperon is there, then is the hyperon star. Similarly, model is there considering some part of hyperon star, some part of the neutron star, and the strange star also. So why neutron star is so important? So it's the important thing, why it is so important for the nuclear physics. So it's provide a unique natural laboratories to test the nuclear force under extreme condition of isospin. So what is the extreme condition of isospin? Because we already first I have told that it is a neutron star, means the maximum amount of neutrons are present, and a very less amount of protons and other particles are there. So there is isospin asymmetry is there, and this isospin asymmetry is very high. It's not like the finite nucleus where the isospin asymmetry is very small. And also the density, which has the density is 5 to 6 times of the density of the nuclear matter. Nuclear matter means, you just imagine the central density of a heavy nucleus like a PB lead nucleus, and the central density it will be the 5 to 6 times of that central density. And we cannot create such density in the artificial laboratory. So it is nature is very kind to us. He has given us a very beautiful laboratory to test our nuclear theory there. So that's why neutron star is very important for us. And then come to the hyperon star. So for the hyperon star, so when the density goes on increasing, then you know that the proton and neutrons are the high fermions, so they obey the Pauli explosion principle, and the next fermions cannot the more than two fermions cannot stay in a one state. So if you further compress the systems, the next fermions will go to the next energy level. So in that way, their Fermi energy goes on increasing. At certain conditions, you will find that the Fermi energy of their nucleons, well, like proton and neutrons, will be exceed the rest mass energy of the hyperons, like lambda, cascade, and sigma hyperons. So then the hyperon will be produced. So generally, the hyperons are produced at the central density 2 to 3 times of the nuclear matter density. You will find hyperons, and just for the information. So in Greek mythology, the hyperons comes from this word, I think, hyperion, and which is in Greek mythology it is described as the 12th son of the sun and earth. Actually, this one is sky and sky and earth, and so next. The matter inside the Newton star is very different from the terrestrial environment. So because of the high density and isospin, this makes the environment is very different from our laboratory environment, and we cannot create that things up to our technical facilities not there to create such things in the laboratory. So therefore, a good knowledge of equation of states. Therefore, a good knowledge of equation of state required to understand the properties of the knowledge, Newton star. So what does means the equation of state? Equation of state means the variation of the pressure density and the energy density with the baryon density. How the energy and the pressure varies with respect to the baryon density. If you know these things, then you can predict the properties of the neutron star like mass, radius, angular momentum, moment of inertia, all these things, and tidal deformability. And traditionally, we thought that the core of the neutron star is modeled as a beta equilibrated neutron-rich matter, and so mostly neutrons, only few percentage of protons and electrons are there. Due to large value of density, 5 to 6 times of nuclear matter, a new hadronic degrees of freedom are more likely to appear inside the core of the neutron star. So there is a possibility. There is a possibility that new degrees of freedoms can come out inside the neutron star core. The hyperon may appear at 2 to 3 times of the saturation density, but the presence of hyperons lead to a softening of the equation of state and a reduction of the maximum mass. So this is one of the problem actually. When you put the hyperon degrees of freedom inside the neutron star equation of state, it reduces significantly the maximum mass of the neutron star. But we observe very high maximum mass, and also our theory should predict very high maximum mass with hyperon, because it is a logical that with such high density there is a possibility of presence of hyperon. So the recent observation of PSR also and the PSR J0348 plus 0432. This is just number, and this number actually this have to show the coordinate where they situated in the sky, and 2.1 solar mass. So demand a steep equation of state, and it start again the long back hyperon puzzle. Means if you put the equation of state, if you put the hyperon degrees of freedom, the equation of state becomes soft. I will discuss what is soft and steep actually. So the presence of hyperon in the neutron star was considered first time by Amartya Sumanya and in 1960, long back. And 3 different mechanisms that could provide such additional repulsion, because repulsion give the steep equation of state, and it give a maximum mass, increase in maximum mass. So repulsion, the repulsive hyperon interaction, and which is done by the exchange of vector meson, and the inclusion of the repulsive hadronic 3-body forces, and the possibility of phase transition in deconfinement quarters. So I will only limit myself in these things, the exchange of vector meson, because I have I have done some work on these things. So in theoretical formalism, we use the theoretical relativistic mean field formalism to calculate the equation of state. for neutron and hyperon star. I am not going to the technical details of this theoretical formalism. You can find lots of review papers about these theoretical formalisms. Now become very popular and old also. So the main things in the theoretical relativistic formalism that two nucleons interact with each other through the exchange of uh, effective measure like sigma, omega, and rho. And for the Newton star, we consider the sigma, omega, rho, and for hyperon star, we consider the sigma, omega, rho, phi, and another is a sigma star. Actually, I have missed this one. Sorry for that. Sigma star also. Sigma star, like in nuclear, these two things, phi and the sigma star, actually give the one attractive and repulsive interaction between the hyperons because they are the strength measure that they have strangeness quantum number, and the other things have no strangeness quantum. So sigma, omega, rho interact between the nucleons, but the omega and the pi and sigma star interact between the hyperons. So this is our Lagrangian density, typical like Lagrangian density, whatever I have used in my calculation. And so from this Lagrangian equation of Lagrangian density, we using the Euler-Lagrangian equation of motion, we can find different equation of motion for different measures, sigma, omega, rho, phi, and all these things. And we have to solve self-consistent in a numerical method to find out the value of the fields and the density and so on and so forth. And then we calculate the pressure. Then calculate the pressure is used to as a input for the this pressure is used to as input to the TOB equation, and this is the TOB equations. And the TOB equations, when you put these things, we get the mass and the radius of a neutron star. So here I'm showing some picture of graph of what is the steep and soft equation of it. And if you soft and steep means how the vary with the energy density and the pressure density, the slope. And if you slope very high, it is a steep equation of state. It's low, it is a soft equation of state. This one is a steep equation of state, and it give a high maximum mass. And if it is a soft equation of state, which is something like that, it is a low maximum mass. So now come to the nuclear meson interaction strength are obtained. How the point is that how we get the nuclear meson interaction strength. So in nuclear meson interaction strength, we get by fitting the saturation properties of infinite nuclear matter, like saturation density, binding energy at saturation density, incompressibility, L symmetry, and all these things. And but in case of and finite nuclear properties like charge density, binding energy, excitation energy. But we know little about the hyperon interaction or hypermeson strength. So because there is a very few hypernuclear present till now, and because it is not very easy to create in the laboratory the hypernuclei. So only maybe 40 or 42 hypernuclei till date we found, and most of them are lambda hypernuclei. And that's why we follow phenomenological approaches to fit the hyperon interaction, assuming that some effective potential, and some experiment shows that this effective potential will be around -30 to -28 to 30 for the lambda hyperon nucleus. And for other two nucleus, it is also a debatable subject, which what will be the value, but most of the people take this value. So in this for this calculation, I have taken this value, and we fit this sigma x, sigma y. This is the sigma with the hyperon interaction strength and the omega with hyperon interaction strength in such a way that we can reproduce that effective potential. And here I have the parameter set we have used, and the main of to use such a huge number of parameter set is that we want to see the parametric dependency on our result. And unfortunately, we know that the nuclear interaction is completely known. So that's why for a nuclear interaction, we depend upon certain model, and every model has some parameters, and every model has some parameters, and Hello, any problem? Hello.
Yes or no?
Okay. So we have categorized these parameter sets in 5 groups. So depending upon the nature of their interactions, because one parameter set and the other parameters are completely different from each other in many respects, and that's why we divide in basis of their interaction. So we have divided into 5 groups, and these are the saturation properties of their parameter sets. And here I am showing the plot of the mass versus radius graph for neutron star, and you can see that various what is the value of the mass and radius for different parameter sets, and this is the observational maximum observed now. So the mass from 1.9 to 2 solar mass, and you can see that very few parameter set can give this type of calculations result, and you can discard other parameter set on the basis of this observation. And still other boxes are there